Chapter 15. Benzene and Aromaticity. Aromatic was first used to describe some fragrant compounds in early 19th century, and nowadays aromatic compounds refer to those compounds that have certain properties that we are going to talk about in this chapter. Here shows some examples of aromatic hydrocarbons. Most aromatic compounds are made either from high-temperature distillation of coal tar or by heating petroleum at high temperature and pressure over a catalyst. Let's first discuss the naming of aromatic compounds. This table lists common names of some aromatic compounds. These compounds are widely used in laboratory and industry. A methyl group attached to a benzene ring is toluene. Hydroxy group attached to a benzene ring is phenol. Amine attached to a benzene ring is aniline. Methyl ketone attached to a benzene ring is acetophenone. Formaldehyde attached to benzene ring is benzoaldehyde. Carboxylic acid attached to benzene ring is benzoic acid. Two methyls attached to benzene ring is xylene. A alkene, ethylene attached to benzene ring is styrene. Let's now discuss systematic naming of aromatic system. First, monosubstitute benzenes. We call the substituents first, followed by benzene. For example, the first molecule is bromobenzene, the second one is nitrobenzene, and the third one is propylbenzene. If the alkyl group is larger than the benzene ring, remember benzene has 6 carbons. If the alkyl group have 7 or more carbons, then the benzene ring becomes a substituent, which is called a phenol. So this is called a phenol. And in this molecule, the alkyl group have 7 carbons, and therefore this benzene called the phenol group. And because it's on the second carbon, so the molecule is called 2-phenylheptane. Note that benzene itself as a substituent is called a phenol group. Benzene with a CH2 as a substituent is called a benzyl group. When benzene ring contains 2 substituents, they have different names according to the relative positions of the substituents. For example, on the first molecule, we have 2 chlorine on adjacent carbon, number 1, number 2 carbon, and this is called author position, O, simplify as O. In the second molecule, the 2 substituents on number 1, number 3 carbon, and they are separated by 1 carbon, and this is called methyl position, or M. And in the third molecule, the 2 substituents, number 1, number 4, all right, they are separated by 2 carbons, and this is called parallel positions, or P. Okay, so relative to X, and these 2 are called author, and these 2 are methyl, and here is parallel position. When a benzene ring contains more than 2 substituents, first thing we need to do is choose the numbers to get the lowest possible value. For example, in the first molecule, we choose to numbering this way, so that we give number 1 carbon, number 2 carbon, number 4 carbon that contains a substituents. Now, if we go the opposite way, then here is number 1, 2, 3, 4. So you have 1, 3, 4 carbons that are attached to substituents, and that's not the lowest. Okay. Now, after we choose the numbers, then we list the substituents alphabetically with hyphenated numbers. So in this molecule, bromo B is in front of methyl M. and therefore this is called 4-bromo-1,2-dimethyl-benzene. In the second molecule, so first thing you recognize is a hydroxy attached to benzene has a common name called phenol, and therefore we choose phenol as its root name instead of benzene. All right, and then after that, the functional group carbon is automatically chosen as number 1. So 1, 2, 3, 4, 5, and therefore the name is 2,5-dimethylphenol. All right. In the last one, again, you have a benzene with methyl, and that's called toluene. And then the carbon with methyl automatically becomes number 1 carbon. So 1, 2, 3, 4, 5, 6. So it is called 2,4,6-trinitrotoluene, or TNT, as an explosive. In the following, we are going to see some special properties benzene has that makes it aromatic. In Organic 1, you learned that a double bond can undergo electrophilic addition reaction with bromine to form a dibromide. Bromine is a red liquid. When after it reacts, it forms a colorless product. This color change can be used to test if the solution contains a double bond. Now, when we draw benzene, we always draw 3 double bonds, and that suggests that this double bond should react with bromine the same way as a alkene does. However, when we mix bromine or the benzene with a bromine, the color doesn't change. No reaction happens unless we add catalyst ion. Even so, the product is not an addition reaction. When the reaction undergo addition reaction, the pi bond break forms a single bond, and the pi bond adds 2 bromine to form dibromide. But in benzene reaction, the double bond is still there. It's still a benzene ring. Okay, the change is a hydrogen replaced by a bromine. So the reaction is called a substitution reaction. Instead of addition, it's a substitution reaction. And this experiment suggests that benzene is not simply composed of 3 double bonds as the structure suggests. Also in Organic 1, you learned that heats of hydrogenation can be used to measure the stability of alkene. This can be explained by energy diagram. In this energy diagram, the left side is the reactant, which is a double bond. And the right side is the product, which when you add a hydrogen molecule, so the 2 hydrogens add to the double bond form alkane. The difference between the reactants and the product, this is called heat of hydrogenation. Now suppose we have 2 alkenes. One is A here and one is B. Okay. Now because A energy is lower than B, so A is more stable. And if we draw the heat of hydrogenation for A, this is the delta H. And this delta H is smaller than the delta H for B. So the smaller delta H corresponds to a lower energy of alkene, or the more stable alkene. So the conclusion is the smaller the heat of hydrogenation, the more stable the corresponding alkene. Now let's compare these 2 molecules. Okay, the left side is a cis, okay, cis butene, and the right side is a trans butene. The experimenter show the heat of hydrogenation for the first one is -120, and the second one is -116, because the second one has a smaller heat of hydrogenation, and therefore, according to this conclusion, the trans is more stable. Okay, this is attributed to the steric effect between these two methyl groups. This table shows heats of hydrogenation of some alkenes. Tetrasubstituted alkene has a smallest delta H, followed by trisubstituted, and then disubstituted, and monosubstituted. And so the conclusion is the tetrasubstituted is the most stable alkene, and then trisubstituted, disubstituted, and monosubstituted alkene. Now let's compare the heat of hydrogenation of benzene with alkenes. We start with cyclohexene with only one double bond. The heat of hydrogenation is negative 118 kJ per mole. When we go to 1,3-cyclohexadiene with two double bonds, the heat of hydrogenation goes up to negative 230 kJ per mole. And that is almost twice of cyclohexene, which is as expected. Two double bonds, twice heat of hydrogenation. According to this trend, if benzene have three double bonds, then the heat of hydrogenation should be approximately 3 times of the cyclohexene, and that would be negative 356 kJ per mole. The actual measured heat of hydrogenation for benzene is only negative 206, and that's 150 kJ per mole different from the hypothetical structure, which contains 3 double bonds there. Okay, so remember in the last 2 slides we showed that the smaller the heat of hydrogenation, the more stable the compound, the double bond or alkene is. So this results indicates that benzene has 150 kJ more stable, okay, than the hypothetical structure with 3 double bonds. So far we show that benzene does not react as an alkene, and benzene is more stable than a structure with 3 double bonds. So what is really the structure of benzene? Let's first go over a double bond. A double bond is formed by 2 carbon atoms with sp2 hybridized orbitals. Each carbon uses 2 of these sp2 hybridized orbitals to form carbon-hydrogen bond, and the third sp2 hybridized orbital forms carbon-carbon bond, and this bond is called the sigma bond. In each carbon, there is an unhybridized p orbital, which is perpendicular to the plane, and this p orbital forms a pi bond. So a double bond contains a carbon-carbon sigma bond and a pi bond. Now in benzene, we have 6 carbon. Each carbon is sp2 hybridized, and each carbon uses one of the sp2 hybridized orbital to form a carbon-hydrogen bond. 2 of them forms carbon-carbon sigma bond, and there's a unhybridized p orbital, contains 1 electron. And these 6 unhybridized p orbitals are perpendicular to the plane of the ring, forms pi bonds. Note that these 6 p orbitals are all connected. They don't just form a double bond localized here, but also here, here, everywhere. Okay, and this is called conjugated system. Okay, now for this kind of structure, you cannot use one Lewis dot structure to represent this structure, because one resonance Lewis dot structure tells you that you have a double bond, but another single bond. But in the real structure, all these p orbitals are connected. It's just one. It's not a one double bond, a single bond. They are all connected. All right. So therefore, we need two resonance structure to represent this real structure. Let's look at the two resonance forms. The first form tells us that here you have a double bond, but the second structure tells us the same bond is actually a single bond, and therefore the real bond is between a double bond and a single bond. Similarly, this vertical bond is a double bond, but the second structure says it's a single bond. Again, this bond is between a double bond and a single bond, and therefore all the 6 bonds are the same. They are in between a double bond and a single bond, and therefore when you combine these two resonance forms together, it tells you that in benzene all the bonds are the same. They are in between a double bond and a single bond. Another way to represent benzene structure is to use a circle. Now in reality, okay, we only draw one of these two resonance forms to represent benzene, but you should be aware that this is not really the benzene structure. As you know, in atoms, electrons are in atomic orbitals. For example, one s orbital has 2 electrons, and then goes to the higher energy level, 2s orbital, 2p orbital, and so on. In molecules, electrons are in molecular orbitals. Here we show 6 molecular orbitals for benzene. This is the lowest energy molecular orbital. The different color indicates different sign. Red color indicates positive, negative color, blue color indicates negative. And this molecular orbital contains 2 electrons. Above it, you have 2 more molecular orbitals, each have 2 electrons. And that all together is the 6 pi electrons. Above them, you have 6 more molecular orbitals that are empty. In summary, benzene is cyclic and conjugated. It is unusually stable. It has a planar structure, and it undergoes substitution reaction instead of electrophilic addition reaction as seen in double bonds. Now, these properties are not only possessed by benzene, but also by many other molecules. So if a molecule has these properties, and this molecule is aromatic,